We'll start with simple harmonic motion, and then we will see the pendulum first, and then we will move to the spring. But as a general statement for the simple harmonic motion, we can say that a simple harmonic motion exists or is in place when two conditions are completed. You have a periodic motion, means that motion is repeating at a certain period of time, periodic motion. And the second condition is that you have a restoring force that is always toward the equilibrium. So restoring force. This restoring force, it's always going through the equilibrium. Now, for a pendulum, what we have is we have a string that is tied, and we have an object that is tied at the end, tied at the ceiling, one side the string, and on the other side, it's an object with a given mass m. It doesn't really matter what is the mass. Now, this position that you see here, it's known as the equilibrium position. Every time that we are saying in physics equilibrium or suspended or it's a constant speed, what does that mean in terms of forces? How do we translate this in our mind in terms of forces? Is that force net is equal to 0. The object is not moving. So on this case, so what we have is that if we draw the free body diagram on this case, so we will see that the force of gravity of this object is equal to the tension on the string. Okay, equal in magnitude with the tension on the string, but opposite direction, so that they cancel each other. And now what do we do to the spring is we give the spring certain energy, type of energy, and you will tell me what it is. So what do we do is we'll lift the object at a certain height. So now what do we see here is that there is a change on the mechanical energy of the object with mass m. What type of energy are we giving to the object? Okay, gravitational potential. Okay, so let's draw the free body diagram of the object right as we release the object from that maximum height that we are giving ourselves. So the free body diagram at this position will be something like this. Force of gravity is always going down, and then tension will be always along the string starting from the object. So as you see here, the tension has two components, the vertical component and the horizontal component. Okay, so now since the object is not moving up and down because we are bringing the object at a certain height, and then right as we release the object from that height, the pendulum from that height, then what we notice is that the free body diagram is the one that we see here. So right at that moment, the object is not going up. Those two the vertical component of the tension and the force of gravity are equal to each other. What is unbalanced on this situation is the horizontal component of the tension. And this will be toward, as you see here, is toward the equilibrium. Okay, so now we have a restoring force on this position when we bring the object up here. We have a restoring force that is an unbalanced force that is going toward the equilibrium. Is this clear? Now, what do we do is what the object does actually in an ideal situation is that it moves from this position that we brought it up, and then it goes through the equilibrium, and then it hits the other side of the pendulum. You have seen the pendulums as it goes. It hits the other side of the pendulum, and in an ideal situation, what will happen? What will happen is that we'll go at the same height as it was on this position here, the same height. Okay, so this height here is the same as the height that we had on the other side of the pendulum. And then as it goes on this side, it reaches the maximum height, then it goes to the equilibrium again, and then it hits the other side, and then so on. The object is making a periodic motion in an ideal situation. When I say an ideal situation, we are assuming here that there is no loss of energy as a result of the air resistance, which means that we are considering it as a isolated system. So the energy is conserved at any point on of the motion, from point 0, let's say, to point A, to point B, to any point in between this motion of the object. Now you may say that, Miss, this is not true, because if I have a pendulum, the pendulum will do some motions and then will stop. The reason that the pendulum stops is because of the resistance that is experiencing from the air that is surrounding it. It's not that the conservation law of energy doesn't work, or it's not that in an ideal situation where it's a vacuum, let's suppose, you will not see this motion going on forever for as long as we are giving some kinetic energy or some potential energy, and then it moves on. Is this clear? So let's try to do the free body diagram at the other side of the swing of the pendulum, and then we will see that we will have a restoring force as well here. Okay, so let's draw the free body diagram on the other side of the pendulum, and we will see and notice that there is a restoring force as well. So we have the force of gravity that is going down, and then we have the tension that is always following the same principle, starting from the object, going along the string. So as you see here, the string will have two components, the horizontal component and the vertical component. So this is the vertical component, and this is the horizontal component of the tension. And the horizontal component of the tension is unbalanced because the vertical component is canceled out by the force of gravity. So the horizontal component is unbalanced. And this will be, or is, the restoring force. In the same logic as we said on the other side of the pendulum. So now we have the two conditions to be completed. We have a periodic motion that in an ideal situation the object, as soon as we are giving some potential energy, will be moving left and right, will go swinging left and right along the equilibrium position. And we have a restoring force that is toward the equilibrium. So even when we go on the left side, or when we go on the right side of the equilibrium, the restoring force will be always toward the equilibrium. And the restoring force at the pendulum is the horizontal component of the tension of the string. Clear? Now, since we have a periodic motion, that means that we will have to discuss what is period of the motion and what is the frequency of the motion. Frequency of the motion, okay? What is the frequency of the motion? Let's kind of review again what is a period. The period is a time that the object completes one revolution, which means it completes one full circle. So in the case of the pendulum, the time that it goes from point A, that is the highest point, to the equilibrium, goes to point B, that is the highest point on the other side of the pendulum, and come back to point A. So the time that the object completes one full revolution will be the period from A to the equilibrium, to the highest point, back to the equilibrium, back to the starting point. This is the period of the motion. The frequency on the other side is how often do we see, how often do we see that object passing through a certain point in 1 second? If the units for period is seconds, the unit for frequency, and it's known with the lowercase f, is hertz, which is nothing but 1/seconds. And the letter that we recognize the period is t. Now, the relationship between the period and the frequency is they are inverse of each other. So period is equal to 1/f, or you can say f is equal to 1/t. You have this formula on your formula sheet. Can you please check them? So now when we have a pendulum, the period of the pendulum is not dependent on the mass that the object has, the object that is at the string, the other side of the string has. So when we have a pendulum that we have an object with mass m, the period of the pendulum is independent of the mass that the object has. What is dependent on, though, is the gravity, the universal, or the acceleration due to gravity at that particular place that you are dealing with, and the length of the string of the pendulum. So the formula that we will use to identify the period of a pendulum is 2 pi square root L/g. Let's take a look at this formula for a moment and then discuss what is happening here. So we can say that the period is direct proportion of the square root of L. What does that mean? If you are increasing the length by a factor of 2, then the period will be increased as well, but the factor that the period is increased will be the square root of 2, because length is under the square root. So when we have, again, when we have a length that is decreased by a factor of, let's say, 1/3, then the period will be decreased as well, but will be decreased by a factor of 1/√3 or √3/3, because you multiply both sides by √3 and then you have it √3/3. Or when we have a length that is increased by a factor of 4, then the period will be increased as well, but will be increased by a factor of √4, which is equal to 2. Or when we have a length that is decreased by a factor of 1/9, then the period will be decreased as well by a factor of 1/√9, which is 1/3. Is this clear? The relationship between the period and the length of the pendulum? So now let's take a look at the relationship that the period has with the gravity. So it is 1/the square root of the gravity. So if the gravity is increased, let's say by a factor of 3, then the period will be decreased. And the factor that will be decreased will be 1/the square root of 3. Okay, if you are, let's say, decreasing the gravity by a factor of 9, then what will happen with the period will be increased by a factor of √9, which is equal to 3. So you should be able to identify, especially for the length, what is happening with the period when you are changing the length by a certain factor. Let's take a look at this example here. If a pendulum is 80 centimeters long, what is the period and the frequency of the vibration or the periodic motion So length of the pendulum is 80 centimeters. We have to convert it into meters because those are the international system units. So you can go 0.80 meters. And now they're asking for the period and for the frequency. So the period of the pendulum is 2π the square root of L/g. And we are assuming here that the acceleration due to gravity, or this pendulum, is near the surface of the Earth. So the acceleration due to gravity is 9.81. So we'll have 2π the square root of 0.80 over 9.81. Now in your calculator, please tell me on the chart, what is this? 1.79 seconds. So what this is telling us, this number is telling us that when the pendulum moves from the highest point on the left, let's say, and goes to the equilibrium, go to the highest point on the right, and then it's coming back to the equilibrium, and it's coming to the original position, the time to complete this whole motion is 1.79 seconds. And then from here, the frequency being 1/period will be 1/1.79 seconds, and it is 0.56 hertz. So in 1 second, it completes 0.56 56 of the period. This is the meaning of this number. Is this clear? So let's take a look to this other example here. We have a planet, and Luke found that 50 centimeters pendulum completes 20 swings, in 33.6 seconds. What is the acceleration due to gravity of this planet? Let's I will take a look on this on the formula again. So we have 2 pi the square root L over G, and I will do the calculations or manipulations, I should say, of this formula to isolate for G. So since we have the square root, we square up both sides. And then the squaring up is affecting everything in the formula. So then we will have t squared is equal to 2 to the power of 2 is 4 pi squared, and then we have L over G. And now solving for G, we multiply both sides by G. So then we will have G times T squared is equal to 4 pi squared L. And then as the last step, we divide both sides by T squared. So G will be equals to 4 pi squared L over T squared. Okay, so now do we know what is the period of this particular pendulum? Do we know the time that it needs to complete one complete swing on this case? Please answer on the chat and tell me what it is. So what the problem is giving us is telling us what is the time for 20 swings. However, when we are looking for the period, is the time that it needs to complete one full swing. So then what we will do is we will take the total time divided by the total number of swings. So we will have, on this case, 33.6 seconds divided by 20 swings, and then we will have the time per one swing, that is 1.68 seconds. So this will be the time, the period. Now you can choose to use this formula to do those transformations that I did here, those manipulations that I did here, and then substitute T and substitute the length as converted it in meters. Or you can say that 1.68 is equal to 2 pi the square root of 0.50 over G that you are looking for. And then do all the manipulations and figure out what is G. Now tell me, what is G? So will be 6.99 meters per second squared. You can say 7, it's fine, I don't mind it. Okay, so now let's see another question in which we are finding the acceleration of the pendulum when it is 16 degrees from to the right of the equilibrium position. Okay, so we have a pendulum here that, let's draw the situation. I clear the situational diagram. We have a pendulum that the equilibrium position is somewhere in here. The mass of the object is 0.250 kilograms. And now what we are doing is we are giving the same deal. We are giving some gravitational potential energy, and then we are looking for the acceleration when the pendulum is 16 degrees from the equilibrium position, so to the right of it. So it's 16 degrees is here. Okay, so on the moment that you are looking for a force, that you are looking for an acceleration, the very first thing that should come to your mind is to draw the free body diagram. So, because this tricks you. So as soon as you see the force, what is the force? What is the acceleration? Then you draw the free body diagram. So the object of our interest is the mass of this object here. And then we will have the universal force of gravity that is always going down. And then you will have the tension, which is always starting from the object going along the string. The tension here. Okay. The angle that the tension is creating with the vertical axis is 16 degrees. So this is 16 degrees as well. And then what we do is, since we have a 2D situation, two-dimensional situation, what we do is we draw the free body, the table of components. So the force of gravity is 2.50, no, 0.250 times 9.81 will be with a magnitude of 2.4525. Let's keep everything here, newtons. So now let's build the table of components. It's something that we have done it from day one. So horizontal and vertical. And then we have force of gravity as the forces that the object is experiencing, tension, and force net. So on the horizontal, force of gravity is equal to 0. On the vertical is a negative 2.4525. Tension on the horizontal is this one here. I will draw it with a different color. So is this one here. This is the horizontal component. So will be whatever, it's negative first of all, because it's going in the opposite direction. It's negative whatever is the tension times sine 16 degrees. And then the vertical component is this vector here. It is positive because it's going in the positive direction. T times cosine 16 degrees. And now on the horizontal direction, we will have mass times acceleration with a negative because the object will go in this direction, will move toward the equilibrium in this direction. And on the vertical will be equals to 0 because it is not going up and down. So from the horizontal component, what do we have is tension, negative tension times sine 16 is equal to negative 0.250 times acceleration. And from the vertical, what we have is a negative 2.4525 plus t times sine 16 is equal to 0. So then we have two equations with two variables, tension and acceleration. We start solving it with the equation that has one variable on it, and this equation is equation 2. So from here we find that tension is equal to 2.4525 divided by sine 16. Make sure that the mode of your calculator is on degrees. And then you go divide by sine 16. You will have 8.0 So this will be cosine, and this should be cosine. Sorry. This should be cosine. So 2 point, sorry about that, divide by cosine 16 is equal to 2.551 Newton. So tension will be 2.55 newtons. Sorry about that confusion. And then the unbalanced force here, or force net, is the horizontal component of the tension. So now, from the first equation, we can say that 2.55 times, negative 2.55 times sine 16 is equal to negative 0.250 times acceleration. So from here, we find that acceleration is, let's do the calculation. Yeah, acceleration is 2.81 meters per second squared. Is this clear? So when we discuss the simple harmonic motion, we discuss it from 3 perspectives, let's say. Whether does it satisfy the conditions to complete a simple harmonic motion? And remember, the two are the conditions that it needs to satisfy to complete a simple harmonic motion: to have a periodic motion and to have a restoring force. So we said that in an ideal situation, when we have an isolated system, so no air resistance is affecting the motion, what is happening? The object will move from one point to the other. The pendulum will move from one point to the other along the equilibrium. And then we said that, okay, let's discuss now and see what if there is a restoring force. And the condition for the restoring force has to be that is always toward the equilibrium, because it is making the object to go to the equilibrium. Now, we saw this from the conditions that needs to satisfy. We saw that from the dynamic perspective. So what is the acceleration and what are the forces that the object is experiencing? Now let's take a look at the pendulum from the energy perspective. So we said that when we are bringing the object, the pendulum up at a certain point, what we are doing is we are giving the system, which means the object on this case, gravitational potential energy. So I will draw a pendulum that is a big one so that we can see and add things on it. So this is the equilibrium position, and then we are bringing the object somewhere in here. So by doing this, what we are doing, as we said, is we are giving a gravitational potential energy. So here we have a potential energy for the system. We added a potential energy. As the object, so now the gravitational potential energy is in relation to this level here, which you can call it ground level, or you can say 0 level. So there is no gravitational potential energy at that level. As the object is moving from point A, that is the highest point, this is max, from point A to equilibrium, point 0, what is happening with this gravitational potential energy based on the conservation law of energy that we discussed yesterday? What is happening? Okay, so as it is moving from point A to point 0, that is the equilibrium, this gravitational potential energy is transformed into kinetic energy. Okay, so at equilibrium, what do you have actually is the maximum speed that the pendulum can have. Okay, it's the maximum speed of that the object can have, because all gravitational potential energy that you have here, which is the maximum gravitational potential energy, is converted into a maximum kinetic energy, which will produce the maximum speed of the object. And at any point between A and the 0, at any point here, you will have part of it is kinetic and part of it is potential energy. Is this clear? And now what is happening, the object is moving on the other side. Okay, it's moving on the other side here. So it is reaching again the maximum height on the other side. So let's call this a point B. Now, what is happening with this kinetic energy of the object at the equilibrium, which is the maximum kinetic energy, which is the mechanical energy of the system? What is happening with it? What is happening? It is transformed in what? Okay, so when it is at the maximum height on the other side of the swing, the other side of the equilibrium, what do we have is maximum potential energy. But at any point in between those three extremes, point A, point B, and the equilibrium, at any point we will have both kinetic and potential, both kinetic and potential. Since we have a height from this that we consider ground level, in which we assume in the ground level that the gravitational potential energy is equal to 0, then at any point, point C, point D, we will have both. At point C, we will have kinetic and potential, which is equal to either the maximum kinetic or is equal to maximum potential, because those two are the mechanical energy of the system. And based on the conservation law of energy, the mechanical energy is conserved, is not destroyed, is transformed from one form to the other. And when you see transformed, it is in between this transformation. In between this transformation, you have them both, potential and kinetic, potential and kinetic. Is this clear? Okay, let's take a look now to this example here. A 2 kilogram mass on a string is pulled so that the mass is at 1.274 meters high, higher than the equilibrium. And when it is released, what is the maximum speed of the pendulum? What is the maximum speed that the pendulum will have during the swing? And what is the speed of the pendulum when it is halfway down from its maximum height? So let's deal with the first one. Okay, the first one here is saying to you that you have an object with mass of 2 kilograms. So this is the situational diagram. The object with mass 2 kilograms. It is brought to a height, to a certain height here, of 1.274 meters. Okay, yeah. So now this is where the object is. Now they are asking you, what is the maximum speed that the object, this object with mass 2 kilograms will have? we know from what we just said before that the maximum speed will be at the equilibrium, okay? But even if you don't, just using the conservation law of energy, you can say that this is the initial, and then we will have, at the initial, we will have gravitational potential energy, okay? And mechanical energy of the system, will be equals to the gravitational potential energy. So now, the mechanical energy of the system will be equals to mass times acceleration due to gravity times height. And in our case, will be 2.0 times, we are assuming that this is happening at the surface of the Earth, 1.274. And using your calculator, 2 times 9.81 times 1.247 will be, or 274, not 274, will be 24.997, or you can say it is 25. It's fine. Joules. Okay? Now, this, that is the maximum energy that the system has, is the mechanical energy of the system, is transformed into a kinetic energy. Everything is transformed into kinetic. This will give us the maximum velocity. So this 24.998, whatever, or 25 joules is equal to 1/2 mv max squared. And from here we find what is V max. Will be the square root of 2 times 25 over 2.0. So will be 5.0 meters per second. Meters per second, yes. Okay, good. Is this clear? We will see what is the speed halfway. So when we are saying halfway, and now is it halfway down from its maximum height, it is somewhere in here. So it's a point here where the height is half of max. Half of it, or 1.274 divided by 2. Okay, so at this point, we said that at any point in between, we have both type of energies. So based on the conservation law of energy, we can say that this 25 joules, that is the mechanical energy of the system, is now part of it is kinetic and part of it is potential. Okay, now what do we know in terms of the kinetic energy is 1/2 mv squared. And what do we know in terms of the potential energy is mgh. Now this relationship is equal to 25. Don't forget this. Is the mechanical energy of the system. Now in this side, the squared one, we know what is the mass. We know what g is, 9.81. We know what height is, because height is half of the maximum height, or 1.274 divided by 2. This is the height. And we are looking for the velocity. I bet you that a lot of teachers on Science 10 have done those kind of questions with you when they were talking about the conservation law of energy. But let's go over and solve this. So this will be 1/2 times 2.0 times velocity squared plus 2.0 times 9.81 times 1.274 divided by 2 will be 0.637. From here, we find what is the velocity as, so the speed will be 3. I will say 54 meters per second. And just keep in mind that you cannot have a speed on this situation higher than the maximum speed 5. Okay, so even when you see a question on the test, you cannot have a question that is higher than the maximum speed. Is this clear, guys? Okay, so those are some practice questions. Take a picture of it, and then we will convert the video.